Feedback amplifier. Feedback is the process of taking a portion of an amplifier's output signal and feeding it back into the input. There are two kinds of feedback, positive feedback and negative feedback. In positive feedback, the feedback energy, either voltage or current, is in phase with the input signal and thus it aids the input signal. Negative feedback, the feedback energy is out of phase with the input signal and thus opposes the input signal. This is the block diagram of a positive feedback. This input signal, output signal, and this is the feedback. The input signal is passed through an amplifier which provides a phase shift of 180 degree. Therefore, the input signal and output signal have a phase shift of 180 degree. A portion of the output is feedback to the input through the feedback network. The feedback network provides a further phase shift of 180 degree. Thus, the input and the feedback signal are in phase. Thus, the feedback voltage aids the input signal. But in negative feedback, the feedback network does not provide any phase shift. Thus, the feedback energy and input signal are out of phase with a phase shift of 180 degree. Thus, the feedback energy opposes the input signal. The input signal and feedback signal are in phase in positive feedback, but in negative feedback, the input signal and feedback signal are out of phase by 180 degree. Voltage gain of positive feedback network is A by 1 minus beta A, and that of negative feedback is A by 1 plus beta A. The stability of amplifier decreases in positive feedback, but the stability of amplifier increases in negative feedback. Positive feedback increases distortion, negative feedback reduces distortion. Bandwidth decreases in positive feedback and bandwidth increases in negative feedback. Positive feedback is used in oscillators, but negative feedback is used in amplifiers. Now we are focusing more on negative feedback. Negative feedback returns part of the output to oppose the input, whereas in positive feedback, the feedback signal aids the input signal. This is a feedback amplifier with feedback fraction beta, feedback voltage Vf. Vs is the input signal and Vo is the output signal. If Vf equal to 0, there is no feedback. Therefore, gain is equal to Vo by Vs, that is equal to Vo by Vi. If feedback signal Vf is connected in series with the input, then Vi is equal to Vs minus Vf, since it is negative feedback. Vo is equal to A into Vi, that's equal to A into Vs minus Vf. But Vf is equal to beta times Vo. Therefore, Vo is equal to A into Vs minus beta Vo, or Vo into 1 plus beta A is equal to A into Vs. Vo by Vs is equal to AF, that's equal to A by 1 plus beta A, where A is the open loop gain of the amplifier and AF is the closed loop gain of the amplifier, or gain of the amplifier with the feedback. Advantages of negative feedback. For negative feedback, beta A is greater than 0, and for positive feedback, beta A is less than 0. Reduction in frequency distortion. For a negative feedback amplifier, beta A is normally very much greater than 1. We know AF is equal to A by 1 plus beta A. Since beta A is very much greater than 1, 1 plus beta A is approximately equal to beta A. Therefore, AF is approximately equal to 1 by beta. If the feedback network is purely resistive, the gain with the feedback is independent on frequency. Thus, the frequency distortion reduces in negative feedback. Gain stability. We have AF is equal to A by 1 plus beta A. Taking differential, DAF is equal to DA by 1 plus beta A all square. DAF by AF is equal to 1 by 1 plus beta A dA by A. That means the magnitude of relative change in gain of AF, that is DAF by AF, is reduced by a factor of 1 plus beta A compared to that without feedback, that is dA by A. Thus, gain stability increases with the negative feedback. Reduction of nonlinear distortion. Nonlinear distortion df is equal to d by 1 plus beta a. df is the distortion with feedback. Distortion is reduced by a factor of 1 plus beta a with a negative feedback. These are the two curves. This one is the open loop gain and this is the closed loop gain. This is more or less linear. Thus, there is nonlinear distortion reduction in negative feedback. Bandwidth extension. Here A is without feedback and this is with the feedback. With the feedback, bandwidth is 2f minus 1f, which is bigger than f2 minus f1. Thus, amplifier with negative feedback has more bandwidth than without feedback. Feedback connection types. Both voltage and current can be fed back to the input either in series or parallel. Thus, we can have 4 connection types: voltage in series, voltage in parallel, current in series, and current in parallel. Voltage series feedback. Let us calculate voltage gain. This is a block diagram of voltage series feedback. A fraction of output to voltage is fed back to the input in series. VO is the output, VF by VO is the feedback fraction. Thus VF is equal to beta VO, that is connected in series with the input signal. Voltage gain AF is equal to A by 1 plus beta A. Let us calculate input impedance. This is a detailed diagram of voltage series feedback. Zi is the input impedance, Vi is the input voltage, Vs is the input signal, Vo is the output, gain is Vo by Vi, feedback fraction beta is equal to Vf by Vo, is connected in series. Therefore, input current Ii is equal to Vi by Zi, that's equal to Vs minus Vf by Zi, Vs minus Vf since it is negative feedback. That's equal to Vs minus Vf is beta times Vo by Zi. That's equal to Vs minus beta times Vo is A into Vi divided by Zi. Therefore, Vs is equal to Ii Zi plus beta AVi. That's equal to Ii Zi plus beta AVi is Ii Zi. Zi with feedback, input impedance with feedback is equal to Vs by Ii. That's equal to Zi plus beta A Zi. This is equal to Zi into 1 plus beta A. Thus, input impedance with feedback increases by a factor 1 plus beta A in voltage series feedback. Now, output impedance. Voltage V is equal to IZO plus AVI. Output impedance. The voltage output voltage V is equal to VO plus this voltage. VO is A into Vi and this voltage is I into ZO. Therefore, V is equal to IZO plus AVI. For Vs equal to 0, Vi is equal to minus Vf. V is equal to IZO minus AVF. That is equal to IZO minus A into beta V. ZOF, that is output impedance with feedback, is equal to V by I, that is equal to ZO by 1 plus beta A. That means the output impedance decreases by a factor 1 plus beta A with negative feedback in voltage series feedback network. Therefore, the results are AF is equal to A by 1 plus beta A, ZIF is equal to ZI into 1 plus beta A, ZOF is equal to ZO by 1 plus beta A. Voltage shunt feedback. Here, the output voltage is fed back to the input in parallel to the input voltage. Here, the feedback factor beta is IF by VO, or IF is equal to the current. IF is equal to beta VO. IS is the signal current. IA is the input current. Gain is VO by II. VO is the output. Voltage gain is AF is equal to A by 1 plus beta A. Input impedance. This is a circuit diagram. IS is the signal current. IF is the input current. IF is the feedback current. And beta is IF by VO is the feedback fraction. Therefore, ZIF is equal to VI by IS, that is equal to VI by II plus IF, that is equal to VI by II plus beta VO. Multiplying and divided by II, we have ZIF is equal to ZI by 1 plus beta A. Thus, input impedance with feedback reduced by a factor of 1 plus beta A in voltage shunt feedback. The results are AF is equal to A by 1 plus beta A, input impedance is ZI by 1 plus beta A, and output impedance with feedback is equal to ZO by 1 plus beta A. Current series feedback. This is the block diagram. Beta is Vf by Io. The current is fed back in series with the input. Vf is beta Io. A is Io by Vi. And Zif is Zi into 1 plus beta A. Zof is Zo into 1 plus beta A. Here both input impedance and output impedance increases by a factor of 1 plus beta A. Current shunt feedback. Here the current is connected parallel with the input and feedback factor beta is equal to If by Io, and input impedance with feedback is Zi by 1 plus beta A. Zof is Zo into 1 plus beta A. Thus input impedance decreases and output impedance increases. Comparing feedback connection types, we have 4 connection types: voltage series, voltage shunt, current series, current shunt. Open loop gain A is Vo by Vi, Vo by Ii, Io by Vi, Io by Ii, and input impedance with feedback is increases in voltage series and current series feedback connections. Output impedance decreases in voltage series and voltage shunt feedback. Some practical feedback circuits. Emitter follower. Emitter follower is a buffer stage with high input impedance, low output impedance, and a gain of approximately unity. This is a current series feedback connection. Circuit diagram is this one. Vi is the input signal. R1 and R2 and plus VCC gives the necessary biasing. This is a voltage divider biasing. The output is taken from the emitter and there is no load at the collector of the circuit. The input and output of the circuit are in phase. That's why the name emitter follows the base or emitter follower. DC analysis. We have VB is voltage across R2, that is R2 by R1 plus R2 into VCC. Emitter current IE is equal to VE by RE, that is equal to VB minus VBE by RE. VCE is equal to VCC minus VE. When VCE equal to 0, we have IC saturation, that is equal to VCC by RE. When IC equal to 0, VCE of is equal to VCC. We have the DC load line AB with IC saturation VCC by RE and VCE of at VCC. Voltage gain of emitter follower. This is the emitter follower. The AC equivalent circuit of emitter follower is this one. The VCC is grounded. Thus it is also a common collector configuration. Here the AC resistance of emitter circuit RE is equal to RE prime plus RE. RE is the emitter resistance. RE prime is equal to 25 millivolt by IE. IE is the emitter current. 25 millivolt is the thermal voltage produced at this junction at room temperature. A more detailed connection of emitter follower is this one. R1 and R2 parallel. RE prime is equal to 25 millivolt by IE. This is the emitter current, that is RE, and this is a forward bias diode. IC is approximately equal to IE since there is no collector resistance. The input voltage is applied across AC resistance of emitter circuit, that is RE prime plus RE. Input voltage VI is equal to IE into RE prime plus RE. Output voltage VO is equal to IE into RE. Voltage gain is equal to VO by VI, that is equal to IE RE by IE into RE prime plus RE, that's equal to RE by RE prime plus RE. In practical cases, RE is very much greater than RE prime, so that RE prime plus RE is approximately equal to RE. Therefore, AV is approximately equal to 1. Thus, the voltage gain of an emitter follower is approximately unity. Input impedance of emitter follower. This is an emitter follower with a load RL. This is the equivalent circuit with RE prime as the emitter resistance. RE prime is RE parallel RL. R1 parallel R2 is the base resistor RB, and beta is current gain. Beta is IC by IB. Therefore, IC is equal to beta IB, that is approximately equal to IE. VB is VBE plus VE. ZI is input impedance is RB parallel base impedance, or RB parallel Z base. Z base is equal to VB by IB, that's equal to IE into capital RE prime plus RE prime by IB, that's equal to IC plus IB into RE prime plus RE prime by IB. IC is beta IB, that's beta IB plus IB into RE prime plus RE prime. On simplifying, this is equal to beta plus 1 RE prime plus RE prime. Normally the value of beta is very much higher than 1. Therefore, beta plus 1 is approximately equal to beta. Therefore, Z base is equal to beta into RE prime plus RE prime. Therefore, input impedance Zi is RB parallel beta into RE prime plus RE prime in the case of emitter follower. Output impedance of emitter follower ZO is given by RE prime parallel RE prime plus RI prime by beta, where RI prime is R1 parallel R2 parallel RS. RS is the output resistance of amplifier voltage source. In practical circuits, RE is large enough to be ignored. Therefore, ZO is equal to RE prime plus RI prime by beta. Applications of emitter follower. To provide current amplification with no voltage gain, impedance matching, the high current gain combined with near unity voltage gain makes this circuit a great voltage buffer used for circuit isolation. Darlington amplifier. This is the Darlington amplifier. The emitter of the first transistor is connected to the base of the second transistor, and the collector of both the transistors are connected together. Darlington transistors are available with one collector, base and emitter. Here both the transistors are connected. In Darlington amplifier, IE1 is equal to beta 1 times IB1. Since IE1 is approximately equal to IC1. Beta 1 is the amplification factor of first transistor Q1. Now IE1 is the base current of Q2. That is IE1 is equal to IB2. IE2 is equal to beta 2 times IB2, where beta 2 is the current amplification factor of Q2. That is equal to beta 2 IE1. That's equal to beta 2 into IE1 is beta 1 IB1. Therefore, current gain beta is equal to IE2 by IB1. That's equal to beta 1 beta 2 IB1 by IB1. That's equal to beta 1 into beta 2. Thus, in Darlington amplifier, the net current gain beta is equal to beta 1 into beta 2, much higher than the emitter follower. Input impedance Zi is equal to beta 1 beta 2 Re. It is also much higher than the emitter follower. If we want more input impedance than emitter follower, we can use Darlington amplifiers or Darlington pair, or we can use Darlington transistor. Applications. Extremely high input impedance in some mega ohm range, extremely high current gains several thousands, extremely low output impedance a few ohm.